Look up at the night sky, and you're seeing only a tiny fraction of what's really out there. The stars, the galaxies, even the glowing nebulas, they're just the visible tip of a cosmic iceberg. Because what truly shapes our universe, what holds galaxies together and weaves the vast cosmic web, is something we can't even see: dark matter. This mysterious substance makes up nearly 1/3 of everything in existence, yet it leaves no trace of light, no direct signal for our telescopes to catch. It's the universe's best-kept secret, an invisible force sculpting the cosmos while remaining utterly elusive. But how do we know it's there? And if we can't see it or touch it, how can we unravel its mysteries? That's what we're diving into today, a journey to the edges of our understanding, where the answers might rewrite everything we know about space, time, and the very fabric of reality. From the first clues that hinted at dark matter's existence to the mind-bending experiments trying to catch it in action, we're exploring why this hidden architect of the universe is one of science's greatest puzzles. Ready to uncover the invisible? Let's begin. The story of dark matter begins with a cosmic puzzle that left astronomers scratching their heads. Back in the 1930s, a sharp-eyed Swiss scientist named Fritz Zwicky was studying the Coma cluster, a massive group of galaxies bound together by gravity. But something didn't add up. When Zwicky calculated how fast these galaxies were moving, he realized they were zooming around so quickly that they should have flung themselves apart. The gravity from all the visible stars and gas simply wasn't strong enough to hold them together. There had to be something else, something unseen, providing the extra gravitational glue. Zwicky called it Dunkel Materie, dark matter, but his bold idea was mostly ignored at the time. Decades later, another astronomer, Vera Rubin, stumbled upon the same mystery while studying spiral galaxies. She expected the stars at the outer edges to orbit more slowly, just like planets farther from the sun, but to her shock, stars near the edge moved just as fast as those close to the center. Again, the math didn't work unless there was an enormous amount of invisible matter surrounding each galaxy, exerting a gravitational pull. Rubin's painstaking observations turned Zwicky's fringe theory into undeniable evidence. Suddenly, the scientific world had to confront the reality that what we see in the universe is just the tip of an invisible iceberg. These discoveries didn't just add a new ingredient to the cosmic recipe, they upended our entire understanding of gravity, structure, and the very foundation of physics. Dark matter wasn't just a missing piece, it was the hidden scaffolding holding the universe itself together. And yet, despite all the evidence, it continues to elude direct detection, making it one of the most tantalizing unsolved mysteries in modern science. So what exactly is this mysterious substance shaping our universe? Picture trying to study a city at night by only looking at the streetlights. You'd miss all the buildings, roads, and hidden alleys between them. Dark matter is like that invisible infrastructure, unseen yet holding everything together. Unlike the ordinary matter that makes up stars, planets, and even our bodies, dark matter doesn't play by the same rules. It doesn't shine, absorb light, or collide with other particles the way atoms do. In fact, if a chunk of dark matter passed right through you this second, you'd never feel a thing. Yet its gravitational fingerprint is everywhere. Think of it like the wind. You can't see it, but you see its effects as it bends tree branches or pushes sailboats across water. Similarly, dark matter's gravity warps the fabric of space-time itself, bending the path of light from distant galaxies in a phenomenon called gravitational lensing. It's why galaxies spin faster than they should, and why clusters of galaxies move as if they're being tugged by something unseen. scientists have narrowed down the possibilities to a few leading candidates. One is WIMP hypothetical particles that rarely interact with normal matter except through gravity. Another contender, Axions, are ghostly lightweight particles that might shift between matter and antimatter states. Then there's the wild card. Could dark matter be made of primordial black holes, remnants from the universe's earliest moments? The challenge is that these particles, if they exist, don't behave like anything we've ever detected. They're not just hiding in the shadows, they're fundamentally different from anything in our periodic table. What makes dark matter so revolutionary isn't just its invisibility, it's how it forces us to rethink the rules of reality. Every galaxy we see is like a chandelier hanging from an unseen ceiling, its delicate balance depending on forces we're only beginning to grasp. Unlocking its secrets could do more than solve a cosmic mystery. It might reveal entirely new laws of physics, hidden dimensions, or even clues about how the universe will end. And that's why, after decades of searching, scientists are still chasing this invisible architect because finding it would change everything. Imagine the universe as a vast construction site in its earliest moments, a chaotic soup of particles and energy. But one ingredient held the blueprint for everything we see today, dark matter, while ordinary matter, the stuff that makes up stars and planets, was bouncing around like a frenzied crowd. Dark matter stood still, unaffected by light or radiation. This stillness gave it a unique advantage. Tiny bumps in its distribution, no bigger than quantum fluctuations, became the seeds of cosmic structure. Gravity amplified these imperfections, turning them into deep wells where gas and dust could gather. Over billions of years, those pockets of darkness became the scaffolding for galaxies. Without dark matter, the universe would look radically different. Picture trying to build a skyscraper without steel beams. The visible bricks might clump together, but they'd lack the skeleton to hold them upright. That's the role dark matter plays. Computer simulations of the cosmos reveal something astonishing. When scientists modeled the universe with only ordinary matter, galaxies never form. But add dark matter's gravitational pull, and suddenly, virtual universes mirror our own, complete with swirling galaxies, sprawling clusters, and the delicate filaments of the cosmic web. The evidence is etched into the sky. Take galaxy rotation curves, the way stars orbit the center of spiral galaxies. Without dark matter's invisible halo enveloping them, those outer stars should slow down like planets drifting farther from the sun. Instead, they race along at speeds that defy explanation, held in place by the grip of something unseen. Even more telling is the way galaxies cluster together. They're not scattered randomly, they align in vast sheets and filaments, tracing the outline of dark matter's hidden architecture. Here's the twist: dark matter didn't just help build the universe, it set the rules. Its gravity dictated where galaxies would bloom and where voids would stretch for millions of light years. In a way, we're living in the aftermath of a silent battle between two forces: gravity, powered by dark matter, trying to pull everything together, and the expansion of space, trying to tear it apart. And so far, dark matter is winning. Every galaxy, every cluster, every thread of the cosmic web is a testament to its invisible hand, yet for all its influence, we've never directly seen it. That's the paradox at the heart of cosmology. The force that shaped our universe remains just out of reach, a ghost in the cosmic machine. Just when we thought dark matter was the universe's biggest secret, along comes its enigmatic counterpart, dark energy. If dark matter is the invisible glue holding galaxies together, dark energy is the mysterious force ripping them apart, pushing the cosmos to expand faster and faster. Together, they form a cosmic tug-of-war, with dark matter's gravity pulling structures into existence while dark energy stretches spacetime itself. The numbers are staggering. Ordinary matter, everything we can see and touch, makes up a paltry 5% of the universe. The rest, roughly 27% dark matter, and a whopping 68% dark energy, a pairing that shapes everything from the smallest galaxy to the fate of the entire cosmos. This cosmic duel plays out across unimaginable scales. Zoom in on a single galaxy, and dark matter's gravitational grip is undeniable, keeping stars from flying into the void. But pull back to view the universe as a whole, and dark energy takes center stage, its repulsive force overpowering gravity on the grandest stages. The evidence for this came in the late 1990s, when astronomers studying distant supernova made a jaw-dropping discovery. Instead of slowing down as expected, the expansion of the universe was accelerating, as if some invisible hand was pressing harder on the cosmic gas pedal. That hand, scientists realized, was dark energy. What makes this rivalry so fascinating isn't just the balance of power, it's how little we understand either player. Dark energy could be a property of space itself, a cosmic constant Albert Einstein once proposed and later dismissed, called the cosmological constant. Or it might be something far stranger, like a dynamic field permeating the universe, evolving over time. Some theories even suggest dark energy could grow stronger, eventually tearing apart atoms in a catastrophic Big Rip. Meanwhile, dark matter's particles remain just as elusive, hiding in plain sight despite decades of hunting, yet their interplay holds the key to the universe's ultimate destiny. Will dark energy's push eventually win, scattering galaxies into cold isolation, or could dark matter's pull stage a comeback, collapsing everything back into a singularity? The answer lies in deciphering their hidden natures, a challenge that's reshaping physics itself. Every new telescope, every particle detector, every supercomputer simulation brings us closer to untangling this cosmic knot. And when we do, we won't just solve a puzzle, we'll rewrite the story of existence from the first flicker of the Big Bang to the universe's final breath. Deep beneath the Earth's surface, in abandoned mines and shielded caverns, scientists have built some of the most sensitive detectors ever conceived, not to hunt for gold or rare minerals, but for something far more elusive. These underground labs, like the LUX and Xenon experiments, are designed to catch the faintest whisper of a dark matter particle interacting with ordinary atoms. Imagine trying to hear a single raindrop fall in a thunderstorm. That's the level of precision required. The detectors are filled with ultra-pure liquids like xenon, chilled to extreme temperatures, and surrounded by layers of shielding to block out cosmic rays and other background noise. If a dark matter particle, say a WIMP, happens to bump into an atomic nucleus, the resulting flash of light or ripple of charge could betray its presence. But after years of monitoring, the detectors remain eerily silent, catching nothing but false alarms. Meanwhile, halfway across the world, the Large Hadron Collider smashes protons together at nearly the speed of light, recreating the fiery conditions of the early universe. The hope that in these violent collisions, dark matter particles might briefly flicker into existence before vanishing again, leaving behind only an imbalance in the energy signatures. It's like trying to reconstruct an invisible animal by studying its footprints, except these footprints vanish almost instantly. So far, the collider has uncovered no definitive traces, but every new run at higher energies brings fresh possibilities. Then there's the cosmic detective work, scanning the skies for indirect clues. When two dark matter particles collide, they might annihilate each other, releasing a burst of gamma rays or other high-energy signals. Telescopes like the Fermi Gamma Ray Space Telescope scour the galaxy for these telltale flashes, particularly in regions dense with dark matter, like the centers of galaxies or dwarf companions orbiting the Milky Way. Some tantalizing blips have appeared, unexplained excesses of gamma rays from certain regions, but none conclusive enough to declare victory. The deeper the mystery grows, the more creative the searches become. Some teams are tuning into the faint radio waves that Axions might emit in the presence of strong magnetic fields. Others are repurposing ancient minerals, like those found deep in Earth's crust, as natural dark matter recorders, scanning them for microscopic trails left by passing particles over millions of years. Even everyday materials, like the sapphire crystals in precision clocks, are being scrutinized for tiny vibrations that could betray dark matter's presence. What's remarkable isn't just the scale of the hunt, it's how each dead end seems to spark new ideas. Every null result tightens the constraints, forcing physicists to rethink their assumptions. Maybe dark matter isn't made of WIMP or Axions after all. Maybe it's something stranger, something that interacts with ordinary matter even more weakly than we imagined, or not at all. Or perhaps we're missing a fundamental piece of the puzzle, a flaw in our understanding of gravity itself. One thing's certain, the moment dark matter is unmasked, whether in a lab, a collider, or the depths of space, it won't just solve a cosmic riddle. It'll crack open a new chapter in physics, revealing laws of nature we've never dreamed of. Until then, the search continues, a testament to human curiosity and our refusal to accept that the universe's greatest architect might stay hidden forever. Here's a phenomenon so strange it seems ripped straight from science fiction light, bending around invisible cosmic obstacles, as if space itself were a funhouse mirror. This is gravitational lensing, dark matter's calling card written across the sky. Picture a distant galaxy's light traveling billions of years to reach us, only to twist and flare as it passes through a hidden veil of dark matter. The result, stretched smears of light, duplicate images of the same star system, or perfect Einstein rings, celestial halos formed when the alignment is just right. The Hubble Space Telescope's snapshots of these cosmic mirages aren't just beautiful, they're forensic evidence, revealing dark matter's ghostly fingerprints. Take the galaxy cluster Abell 1689, one of the most massive structures we've observed. Its gravity, boosted by an unseen reservoir of dark matter, warps spacetime so dramatically that it magnifies and distorts galaxies far behind it, like a lens of cosmic proportions. By measuring these distortions, astronomers perform a kind of interstellar accounting, tallying up the cluster's total mass. The verdict, the visible stars and gas are mere decoration, outweighed 5-to-1 by dark matter's invisible bulk. But gravitational lensing does more than confirm dark matter's existence, it maps its architecture. Just as ripples on a pond's surface betray the shape of submerged rocks, the patterns of bent light trace dark matter's scaffolding. Some clusters show dark matter clumped exactly where galaxies sit, while others reveal eerie offsets, as if the invisible skeleton doesn't quite line up with the visible body. These mismatches hint at something even stranger, that dark matter might interact with itself in ways we don't yet understand, or that our grasp of gravity needs rewriting. The most astonishing part, this technique lets us study dark matter without ever seeing it directly. By combining lensing maps with other observations, like the cosmic microwave background, scientists have pieced together dark matter's role in shaping the universe's large-scale structure, its filaments, voids, and clusters all sculpted by an unseen hand. And with next-generation telescopes like the James Webb and the upcoming Vera Rubin Observatory, we're on the verge of charting this invisible terrain in unprecedented detail. Every distorted galaxy, every warped quasar image is a breadcrumb leading us closer to understanding the universe's hidden blueprint. Sometimes the universe hands us a perfect experiment, a cosmic crash so violent, so revealing, it shatters old assumptions. That's exactly what happened with the Bullet Cluster, two galaxies colliding at millions of miles per hour, leaving behind a cosmic crime scene that changed physics forever. Here's why this smash-up is such a game-changer. When these clusters plowed through one another, their stars, like tiny grains of sand, sailed right past each other, barely affected. The hot gas between them, though, got caught in the cosmic wreckage, glowing brightly in X-rays. But here's the kicker. When scientists mapped the cluster's total mass using gravitational lensing, the heaviest parts weren't where the gas was. They were offset, hovering near the stars, invisible to telescopes, that missing mass, dark matter, moving through the chaos like a ghost, completely unharmed. This wasn't just another hint, it was proof. If dark matter were just an illusion caused by our misunderstanding of gravity, the mass and the gas would have stayed glued together. Instead, the Bullet Cluster showed dark matter behaving like a separate, physical substance, one that doesn't interact with light or ordinary matter except through gravity. It's as if you threw two handfuls of glitter into a fan. The glitter stars would scatter, the air gas would swirl, but something unseen, dark matter would keep coasting straight ahead, unbothered. The implications ripple across cosmology. Alternative theories, like modified Newtonian dynamics, struggle to explain this separation, why the gravity bends light where there's no visible mass. Yet the Bullet Cluster's dark matter halo lines up perfectly with the lensing maps, like a shadow finally revealing its shape. Even more compelling, we've since spotted other merging clusters, like the Musket Ball Cluster and Abel 520, showing the same eerie disconnect between light and mass. Each one reinforces the same message: dark matter isn't a placeholder for our ignorance, it's real, it's out there, and it's sculpting the universe while remaining utterly, frustratingly invisible. But the Bullet Cluster did more than confirm dark matter's existence, it exposed how little we know about it. The way it streamed through that collision suggests it might not even interact with itself, unlike normal matter that slows and clumps. That's why physicists are now racing to recreate such cosmic crashes in supercomputer simulations, tweaking the rules to see which versions of dark matter match what we observe. Every pixel in those simulations is a question. Are we missing something fundamental, or is the universe just waiting to surprise us again? One thing's certain: when the next great collision lights up the sky, we'll be watching, ready to decode another chapter in dark matter's elusive story. What if dark matter isn't the answer at all? A small but passionate group of scientists has spent decades challenging the mainstream view, arguing that the cosmic anomalies we blame on invisible matter might actually point to something even more radical, a flaw in our understanding of gravity itself. Enter modified Newtonian dynamics, or MIND, a theory that tweaks the rules of gravity to explain why stars on the outskirts of galaxies rotate faster than expected without invoking dark matter. At first glance, it's an elegant solution. Instead of filling the universe with unseen particles, maybe we've just been calculating gravity wrong at galactic scales. MIND proponents point to its success in predicting the rotation curves of spiral galaxies with stunning precision, something dark matter models often achieve only by fine-tuning the distribution of invisible halos. Think of it like fixing a misaligned car wheel by adjusting the steering mechanism rather than inventing an entirely new type of tire. But here's where the theory hits a snag. When confronted with phenomena like the bullet cluster, where gravity clearly comes from something other than visible matter, Min stumbles. It can't easily explain why the mass and the gas separate so dramatically in these cosmic collisions, nor does it account for the intricate patterns etched into the cosmic microwave background, the afterglow of the Big Bang. Those patterns match dark matter's gravitational fingerprints almost perfectly. The debate grows even thornier when you consider galaxy clusters, where Mind requires adding some form of invisible matter anyway, effectively reinventing dark matter under a different name. It's like trying to remove a stubborn stain by painting over it, only to realize you've just created a new mess. Yet even as evidence piles up in favor of dark matter, Mind isn't without value. Its very existence forces physicists to question assumptions, test boundaries, and sharpen their models. Every time dark matter theorists adjust their simulations to match new data, they're indirectly answering Mind's biggest critique, that science shouldn't cling to invisible solutions without exhausting all other possibilities. So where does that leave us? For now, the scales tip heavily toward dark matter. It's the only framework that consistently explains everything from galaxy rotations to the universe's large-scale structure. But the beauty of science lies in its willingness to entertain alternatives, to chase down every lead, even the ones that seem like long shots. Because whether dark matter is confirmed tomorrow or dethroned by a new idea, the pursuit itself reshapes our understanding of the cosmos. And in that sense, theories like Mind aren't roadblocks, they're stepping stones, pushing us toward a deeper, richer vision of how the universe truly works. Run your fingers across a frosted window pane, and you'll trace delicate branching patterns, tiny veins of ice spreading outward like frozen lightning. Now imagine that same intricate design, but scaled up to span billions of light years. That's the cosmic web, the universe's grandest structure, woven together by dark matter's invisible threads. This colossal network isn't just a backdrop for galaxies. It's their birthplace, their highway system, their gravitational blueprint. Supercomputer simulations like the Millennium Run bring this hidden architecture to life. Picture trillions of dark matter particles, each a speck in a digital universe, set in motion by the laws of physics. Hit fast forward, and over 13 billion simulated years, those particles clump and stretch, drawn together by gravity's relentless pull. What emerges is breathtaking, a labyrinth of glowing filaments, dense knots where galaxy clusters congregate, and yawning voids so empty they could swallow thousands of Milky Ways. The resemblance to a spider's web is uncanny, but this isn't silk holding the structure together. It's dark matter's gravity, the unseen hand sculpting the universe's largest features. The voids tell their own story. These sprawling deserts of near-nothingness, some stretching hundreds of millions of light years, aren't random. They're the flip side of the cosmic web's design, regions where dark matter's gravitational tides have drained away not just visible matter, but even the faintest wisp of intergalactic gas. Meanwhile, where filaments intersect, galaxies pile up like cars at a cosmic crossroads. The Virgo cluster, our local hub of over 1,000 galaxies, sits at one such crossroads, anchored by dark matter's gravitational keel. What's astonishing is how perfectly this simulated web matches reality. When astronomers map the positions of millions of galaxies, their distribution mirrors the simulations with eerie precision, like comparing a fingerprint to its match. Even the cosmic microwave background, the afterglow of the Big Bang, bears the imprint of this web's infancy. Those faint temperature fluctuations, they're the seeds of future filaments, quantum ripples amplified by dark matter's gravity over eons. Yet for all its scale, the cosmic web isn't static. It's a living, evolving structure. Galaxies surf along filaments toward clusters in a slow-motion river of dark matter, while the web itself stretches and twists as the universe expands. Somewhere in that vast network, dark matter is still knitting new threads, orchestrating the birth of galaxies we'll never see, and that's the humbling truth. We're not just observers of this web. We're part of it, riding a tiny strand in an infinite tapestry whose full design we're only beginning to trace. Imagine trying to recreate the entire universe in a box, not just stars and galaxies, but the invisible scaffolding that binds them together. That's what supercomputers are doing right now, running digital universes where dark matter's secrets unfold at lightning speed. Take the Elusiveness TNG project, one of the most ambitious simulations ever attempted. It doesn't just track dark matter's gravitational pull, it layers in the chaotic dance of gas, the birth of stars, even the explosive feedback from supermassive black holes. The result, a virtual cosmos that mirrors our own with uncanny accuracy, from the delicate swirl of spiral galaxies to the vast voids between them. These simulations aren't just pretty visuals, they're scientific crucibles. By tweaking the rules, say, adjusting how dark matter interacts with itself, researchers can test theories against real-world observations like a cosmic game of trial and error. When a simulation spits out galaxies that look eerily like the Milky Way, or predicts gravitational lensing patterns we later spot in telescope data, it's a silent triumph. Suddenly, abstract equations translate into tangible cosmic structures, validating decades of hypotheses. But here's the twist: sometimes these digital universes surprise us. Certain simulations suggest dark matter might form ultra-dense clumps within galaxies, or that its distribution could explain mysterious flares from distant quasars, hints that real-world astronomers then rush to investigate. The scale of this computational effort is staggering. Projects like Eagle and Millennium require millions of CPU hours, crunching numbers so vast they'd take ordinary computers centuries to process. Every pixel in these simulations represents thousands of light years, every calculation a snapshot of cosmic evolution over billions of years. And as supercomputers grow more powerful, they're revealing finer details, like how dark matter's subtle fluctuations might influence the very first stars, or why some galaxies end up with bizarre, lopsided shapes. Yet for all their sophistication, these models have limits. They can't yet capture the quantum weirdness that might govern dark matter at the smallest scales, nor can they definitively say what it's made of. That's where the real synergy begins. Supercomputers narrow the possibilities, guiding physicists toward the most promising targets for lab experiments and space telescopes. It's a feedback loop between digital and physical exploration, one where every failed simulation is as valuable as a success, pruning dead ends from the tree of cosmic possibilities. What's thrilling is how far we've come. A century ago, dark matter was a glimmer in Fritz Zwicky's calculations. Today, we're building entire universes to understand it, pushing hardware and software to their limits in a quest to render the invisible visible. And with next-gen, exascale computers on the horizon, capable of quintillions of calculations per second, we're on the verge of simulating dark matter with precision that could finally crack its code, revealing not just how it shapes galaxies, but what it truly is. To understand dark matter's role in the universe's infancy, we need to rewind to a time before stars, before galaxies, even before light could travel freely through space. The cosmic microwave background, or CMB, is our window into that primordial era, a faint glow left over from when the universe was just 380,000 years old. But this isn't just any old light. Embedded in its subtle temperature variations, patterns no hotter or colder than a few millionths of a degree, lies the blueprint for everything we see today. And those patterns, they were etched by dark matter's invisible hand. Think of the early universe as a pond on a windless day. Dark matter's gravity created tiny ripples in the cosmic fabric, denser regions where particles clustered ever so slightly. Ordinary matter, buffeted by radiation pressure, couldn't settle into these ripples right away. It was like trying to build sandcastles in a hurricane. But dark matter, unfazed by light's push and pull, anchored these fluctuations, giving structure a foothold. Over millions of years, those infinitesimal wrinkles grew, deepening into gravitational wells where gas could finally gather, collapse, and ignite the first stars. The Planck spacecraft's map of the CMB is like a fingerprint of this process. Its precision measurements reveal how dark matter's distribution, 27% of the universe's total density, aligns perfectly with the temperature variations we see. The hottest spots, future galaxy clusters, the coldest, the seeds of cosmic voids. It's astonishing how well these ancient imprints match the universe we observe today, as if the CMB were a coded message predicting where galaxies would bloom billions of years later. What's even more remarkable is how dark matter's influence transcends scale. Those quantum-sized ripples in the early universe stretched across unimaginable distances, evolving into the cosmic web's filaments and nodes. Without dark matter's gravitational stability, the universe might have remained a featureless soup, never coalescing into the dazzling structures we admire through telescopes. The CMB doesn't just tell us dark matter exists, it shows us how, from the tiniest fluctuations to the grandest galaxy clusters, this mysterious substance orchestrated the cosmos's very architecture. And that's why missions like Planck are more than just satellites. They're time machines, letting us peer back to the moment dark matter's invisible threads began weaving the tapestry of everything. Among the universe's most elusive particles, neutrinos are the ultimate cosmic ghosts, streaming through space, slipping through planets, even passing through you at nearly the speed of light without leaving a trace. Billions of them race through your body every second, yet you'd never know it. Their near weightless, almost non-interactive nature might sound familiar after all. These are the same qualities that define dark matter. So could neutrinos be the missing piece of the puzzle? At first glance, the fit seems promising. Like dark matter, neutrinos don't clump around galaxies the way stars and gas do. They're more like a faint, uniform mist permeating the cosmos. And just as dark matter barely interacts with ordinary matter, neutrinos famously ignore almost everything in their path. In fact, it took scientists decades to detect them at all, even though they're produced in abundance by nuclear reactions in the sun, supernova, and even bananas thanks to their potassium content. Yet there's a catch. Neutrinos are simply too light to be the sole explanation for dark matter's gravitational heft. The combined mass of all known neutrinos barely scratches the surface of what's needed to hold galaxies together. Imagine trying to anchor a ship with a spider's web. It just doesn't add up. That's why most researchers believe neutrinos can only account for a tiny fraction of dark matter's total influence. But studying them has still taught us invaluable lessons about how elusive particles behave on cosmic scales. Experiments like IceCube, a detector buried deep in Antarctic ice, are hunting for high-energy neutrinos from distant cosmic cataclysms. When one of these particles does, on rare occasion, collide with an atom, it creates a fleeting burst of light, a signal that helps physicists trace its origin and properties. These observations reveal something profound. Neutrinos, while not dark matter's primary architect, are part of a broader family of shadowy particles that defy easy detection. And that's what makes them so fascinating. Even if they're not the answer, neutrinos remind us that the universe is teeming with phenomena that challenge our understanding. They're proof that matter can exist in forms we're only beginning to grasp, hinting that dark matter might be stranger still. So while we haven't found the smoking gun yet, every neutrino we detect is another clue in a much larger mystery, one that could rewrite the rules of physics itself. Among the many dark matter candidates, Axions stand out as a particularly elegant solution not just to the cosmic missing mass problem, but to one of particle physics' deepest puzzles. These hypothetical particles first emerged from theorists' attempts to explain why the strong nuclear force, which glues atomic nuclei together, obeys a perfectly balanced symmetry. Without Axions, quantum calculations suggest the universe should be filled with bizarre electric dipole moments, effects we've never observed. Their introduction in the 1970s was a stroke of mathematical brilliance. Axions would act as nature's reset button, quietly restoring balance to quantum equations while remaining virtually undetectable. But here's where things get cosmic. If Axions exist, they wouldn't just tidy up particle physics, they might also be the elusive substance shaping galaxies. Picture them as an invisible ocean, trillions of times lighter than electrons, yet so abundant that their collective gravity could outweigh all visible stars and gas. Unlike WIMP, which behave like discrete particles, Axions would exhibit wave-like properties, oscillating through space with a rhythmic flow that could theoretically be tuned in like a radio signal. This dual role, as both cosmic architect and quantum peacekeeper, makes Axions searches utterly unique. Laboratories like the Axion Dark Matter Experiment, or ADMX, have turned this theory into a high-stakes treasure hunt. Their tool of choice, a supercooled cavity bathed in a powerful magnetic field, the idea is that if Axions drift through this chamber, the magnetic field might coax them to convert into faint microwave photons, a whisper of light where there should be darkness. It's like trying to hear a single note played in an empty concert hall, with instruments sensitive enough to detect energy shifts tinier than a quadrillionth of a watt. The challenge is that Axions could span a vast range of possible masses, requiring scientists to scan through frequencies methodically, like turning a dial millimeter by millimeter across the entire radio spectrum. Early results have yet to strike gold, but upgrades using quantum amplifiers are sharpening ADMX ears to unprecedented levels. Meanwhile, other approaches are emerging, like the haystack experiment, which borrows techniques from quantum computing to boost sensitivity, or astrophysical searches looking for Axions' subtle influence on starlight and black hole emissions. What makes this hunt so compelling isn't just the potential payoff, it's how Axions straddle two worlds. Finding them wouldn't just fill the dark matter gap, it would validate a profound connection between the quantum realm and cosmic structure, showing how puzzles at the smallest scales might hold keys to the universe's grandest mysteries. And that's the beauty of Axion research. Even the quietest particles could end up telling the loudest story. If dark matter has a poster child, it's the WIMP, short for weakly interacting massive particles. These hypothetical heavyweights are the leading candidate to explain the universe's missing mass, and for good reason. Picture a particle born in the chaotic aftermath of the Big Bang, massive enough to tug on galaxies with its gravity, but so shy it barely acknowledges ordinary matter's existence. That's the essence of a WIMP, a cosmic introvert drifting through walls, planets, even you, without a trace. What makes WIMP so compelling isn't just their theoretical elegance, it's how neatly they fit into the puzzle. According to leading models like supersymmetry, WIMPs should have been forged in the early universe's extreme heat, leftover relics from a time when energy and matter were indistinguishable. As the cosmos expanded and cooled, these particles would have frozen out, their numbers stabilizing into the invisible sea we now call dark matter. The math is almost too perfect. If WIMP exist at the predicted mass and interaction strength, their abundance would precisely account for the gravitational effects we observe. It's as if the universe left us a receipt, and WIMP are the items circled in red, yet for all their promise, WIMP have stubbornly refused to show up in detectors. Experiments like LUX Zeppelin and Panda X operate miles underground, shielded from cosmic noise, waiting for the telltale recoil of an atom struck by a passing WIMP. These detectors are marvels of engineering, ultra-pure tanks of xenon or argon chilled to frigid temperatures, where even a single flicker of light could signal a collision. But after years of running, the results have been eerily quiet. Each new, more sensitive experiment tightens the constraints, narrowing the range where WIMP could still be hiding. The hunt has forced physicists to confront an uncomfortable possibility. What if WIMP are even more elusive than we imagined? Some theories suggest they might interact through forces beyond the standard model, making them invisible to current detectors. Others propose they're not particles at all but something stranger, like macroscopic, dark blobs that slip through conventional nets. The irony is thick, the very quality that makes WIMP a perfect dark matter candidate, their reluctance to interact, also makes them nearly impossible to catch. But here's the twist, every null result is still progress. With each failed detection, scientists refine their models, ruling out swaths of theoretical territory and inching closer to the truth. WIMP may yet be out there, lurking just beyond our grasp, and if they are, their discovery wouldn't just solve the dark matter mystery, it would tear open a new chapter in physics, revealing a hidden sector of particles and forces that shape the cosmos in ways we've only begun to dream. Deep beneath Italy's Gran Sasso mountain, a decades-long mystery pulses in the darkness. The DAMA/Libra experiment has spent years collecting data with a bold claim that it's catching the faint whisper of dark matter particles brushing against atoms in its detector. But here's the catch, the signal they see isn't steady. It rises and falls in a yearly cycle, peaking every June and dipping in December, as if the Earth's journey around the sun is sweeping us through a river of invisible particles. At first glance, it's a compelling story. After all, our planet orbits at over 100,000 kilometers per hour, so if the Milky Way is bathed in dark matter, we'd expect to move through denser patches at certain times of year. DAMA team insists their findings, spanning multiple detector upgrades and 20 years of observations, can't be dismissed as mere coincidence, yet the scientific community remains sharply divided. No other experiment from the ultra-sensitive LUX in South Dakota to xenon beneath the Swiss Alps has seen anything resembling DAMA signal. Critics point to a parade of potential culprits, subtle seasonal changes in the lab's environment, fluctuations in cosmic ray interference, even the movement of groundwater altering background radiation. Some have proposed more exotic explanations, like interactions with atmospheric neutrinos or an unexpected property of the detectors, sodium iodide crystals themselves. The debate has grown so heated that independent teams have built near-identical experiments, like COSINE in South Korea and ANICE in Spain, explicitly to test DAMA results. So far, their data shows no sign of the telltale annual modulation. What makes this controversy so fascinating isn't just the scientific stalemate, it's what's at stake. If DAMA is right, we're glimpsing dark matter's first direct fingerprint, a discovery that would rewrite physics textbooks overnight. But if it's wrong, the implications are equally profound. A null result after decades of searching would force physicists to reconsider not just one experiment, but the very strategies we've used to hunt for dark matter. Are we looking for the right particles in the wrong way? Could dark matter interact with ordinary matter through forces we haven't yet imagined? The resolution, whenever it comes, will be a watershed moment. Either a lone Italian lab will triumph where billion-dollar projects have come up empty, or a cautionary tale will emerge about the perils of measurement artifacts in ultra-sensitive experiments. For now, the data keeps flowing, detectors keep listening, and the question lingers: is DAMA seeing the universe's most elusive substance, or just the echo of its own apparatus? The answer could redefine our search for the invisible, or send us down an entirely new path. Black holes, cosmic vacuum cleaners that devour light itself, might seem like an unlikely candidate for dark matter. Yet some scientists wonder if the answer to one mystery could lie within another. What if dark matter isn't made of exotic particles, but instead consists of countless tiny black holes, forged in the chaos of the early universe? These hypothetical objects, known as primordial black holes, could have formed not from collapsing stars, but from the extreme density fluctuations in the first moments after the Big Bang. Unlike their stellar counterparts, these ancient relics could be as small as an atom or as massive as a planet, drifting unseen through the cosmos like invisible boulders in a dark river. The idea isn't as far-fetched as it sounds. When astronomers search for primordial black holes, they use a technique called microlensing, watching for the telltale flicker of a distant star as an invisible object passes in front of it, warping spacetime like a magnifying glass. Some projects, like the Subaru telescope's Hyper-Suprime Cam survey, have scanned millions of stars for these elusive flashes. So far, the results are sparse, suggesting that if primordial black holes exist, they can't account for all of dark matter's gravitational grip. But there's a tantalizing twist. Gravitational wave detectors like LIGO have picked up mergers of black holes with masses that don't quite fit the usual stellar formation models. Could these be primordial black holes, remnants of the universe's fiery birth? The challenge is that black holes, even primordial ones, leave traces. They'd heat interstellar gas as they pass through it, distort the cosmic microwave background, or even evaporate over time due to Hawking radiation, a process that would produce a detectable burst of energy. Yet none of these smoking guns have appeared, putting tight constraints on how much of dark matter could realistically be hidden in these ancient objects. Current estimates suggest they might make up, at most, a tiny fraction of the total. Still, the possibility lingers, a ghost at the edge of cosmology's understanding. If even a small percentage of dark matter turned out to be primordial black holes, it would rewrite the story of the early universe, revealing a time when space itself was a seething cauldron of gravitational collapse. It would also blur the line between two of physics' greatest puzzles, dark matter and black holes, suggesting that the answers we seek might be hiding in the shadows of each other. Until then, the hunt continues, not just for invisible particles, but for the echoes of black holes born in the dawn of time. The hunt for dark matter is entering a new golden age, armed with technology so advanced it would seem like science fiction just a decade ago. Next-generation experiments like LUX Zeppelin, or LZ, are pushing sensitivity to once unthinkable levels, its tank of ultra-pure liquid xenon poised to catch the faintest flicker of a WIMP collision. Meanwhile, Usidium, buried deep in a Minnesota mine, employs cryogenic detectors so precise they can sense a single atomic nucleus recoiling from a dark matter particle's passage. And then there's the Cherenkov Telescope Array, CTA, a global network of over 100 telescopes designed to scan the skies for gamma rays that might betray dark matter annihilations in space. These aren't just incremental upgrades, they're leaps into uncharted territory, probing interactions 1,000,000 times weaker than anything we've searched for before. But the revolution isn't confined to Earth. Euclid, the European Space Agency's dark matter mapper, orbits with a singular mission to chart the invisible scaffolding of the cosmos across 10 billion light-years. Its high-precision instruments will measure the subtle distortions of galaxies, tracing dark matter's gravitational fingerprints with unprecedented clarity. Imagine uncovering the universe's hidden skeleton not by spotting the bones themselves, but by seeing how they bend the light around them. Euclid's data could reveal how dark matter's distribution has evolved over cosmic time, offering clues about its fundamental nature, whether it's cold, warm, or something even stranger. On the cutting edge, quantum sensors are rewriting the rules of detection. Devices like superconducting qubits and atomic magnetometers operate at scales so tiny they can sense disturbances from a single quantum event. Pair these with AI-driven analysis, sifting through mountains of data to spot patterns human eyes might miss, and you've got a recipe for breakthroughs. Machine learning algorithms are already flagging anomalies in telescope images or particle collision data that could hint at dark matter's signature, like finding a whisper in a hurricane. What's exhilarating isn't just the technology, but the timeline. For the first time, scientists are cautiously optimistic that an answer might lie within our lifetime. Whether it's a definitive signal in a lab, a eureka, a moment in a space telescope's data, or an unexpected twist from a quantum sensor, the pieces are falling into place. Every dead end has narrowed the path forward, and every innovation has sharpened our tools. The next decade could deliver what a century of searching hasn't, a glimpse into the invisible realm that shaped our universe. And when that moment comes, it won't just solve a puzzle, it'll open a door to a whole new frontier of physics, where the rules we know might just be the beginning. Galaxies spin with a grace that defies logic, at least the logic we thought we understood. When Vera Rubin trained her telescope on Andromeda in the 1970s, she expected to see stars near the edge moving slower than those closer to the center, just like planets farther from the sun. But the data told a different story. Those outer stars were racing just as fast as their inner neighbors, like cars on a highway, all maintaining the same speed regardless of lane. According to Newton's laws, this shouldn't be possible. The visible mass of stars and gas simply couldn't generate enough gravity to keep those stars from flinging into the void. Rubin's observations revealed something revolutionary. Galaxies are wrapped in vast, invisible halos of dark matter, extending far beyond their luminous edges. Picture a cosmic whirlpool where the water's surface swirls calmly, but beneath it, hidden currents churn with a force you'd never guess from above. That's how dark matter operates. Its gravity grips stars from unseen depths, anchoring them in orbits that would otherwise defy physics. Without this phantom embrace, spiral galaxies like our Milky Way would unravel, their outer stars scattering like embers from a fire, the smoking gun. Galaxy rotation curves graphs plotting orbital speeds against distance from the center. In a universe governed by visible matter alone, these curves would dip sharply at the edges. Instead, they flatten out, a silent testament to dark matter's pervasive influence. This isn't just true for a few oddball galaxies, It's a universal pattern, seen in everything from tiny dwarfs to colossal ellipticals. Even more compelling, when astronomers study galaxies billions of light-years away snapshots of the younger cosmos, they find the same mismatch between visible mass and motion. Dark matter's fingerprints are everywhere, etched across space and time. What makes Rubin's discovery so profound isn't just the evidence itself, but how it upended astronomy's assumptions. Before her work, many scientists clung to the idea that galaxies were mostly what we could see: stars, gas, and dust. But rotation curves shattered that illusion, revealing a universe where light is merely decoration draped over an invisible scaffold. Today, this remains one of the strongest pillars supporting dark matter's existence. Every time a telescope captures the whirl of a distant galaxy, it's not just mapping starlight, it's tracing the contours of something far greater, a shadowy architecture we're only beginning to fathom. And that's the beauty of science. Sometimes, the most profound truths come not from what we observe, but from the mysteries we can't yet see. Computer simulations of cosmic structure paint a vivid picture, a Milky Way not just alone in the void, but surrounded by hundreds of tiny satellite galaxies, each tethered by dark matter's gravitational strings. But when astronomers point telescopes at our cosmic neighborhood, they find far fewer of these dwarf galaxies than the models predict. This glaring mismatch, known as the missing satellites problem, has haunted astrophysicists for decades, revealing a crack in our understanding of how dark matter shapes the universe's smallest structures. The heart of the puzzle lies in the numbers. Sophisticated simulations like Via Lactea and Elvis, which recreate dark matter's behavior with painstaking precision, suggest our galaxy should be orbited by at least several hundred small satellites. Yet we've only confirmed around 60, most of them faint and diffuse. It's as if someone removed 3/4 of the stairs from a spiral staircase. The structure still stands, but the gaps defy logic. Some of these missing satellites might simply be too dim for current telescopes to spot, but that explanation alone doesn't close the gap. One compelling solution shifts the focus from what we can't see to what dark matter itself might be. Traditional models assume cold dark matter, slow-moving, heavy particles that clump easily into small-scale structures. But what if dark matter is warmer, composed of lighter, faster-moving particles? Warm dark matter would smear out those tiny clumps, suppressing the formation of countless dwarf galaxies and leaving behind only the larger satellites we observe. The difference might seem subtle, but it's cosmic. Swap cold for warm dark matter, and those missing satellites could vanish from the simulation without a trace. Yet there's another twist. Maybe the satellites aren't missing at all, just transformed. Astrophysicists point to feedback mechanisms, where the explosive energy of early star formation in these small galaxies blew away their gas, leaving them too dim to detect. Picture a campfire doused with water. The embers still glow, but faintly, easily lost against the night sky. Supernova or radiation from massive stars could have stripped these dwarfs of their star-forming fuel, rendering them nearly invisible against the Milky Way's glare. The stakes here aren't just academic. Each solution, whether tweaking dark matter's properties or rethinking galaxy evolution, carries profound implications. If warm dark matter proves correct, it would upend decades of assumptions about particle physics. If feedback effects dominate, it means our models of star formation need serious revision. Every faint dwarf galaxy discovered, like the recent finds in data from the Vera Rubin Observatory, tips the scales slightly, offering clues to this cosmic whodunit. And as telescopes grow more sensitive, we might finally find the missing pieces or realize they were hiding in plain sight all along, reshaped by forces we're only beginning to understand. The universe isn't just expanding, it's caught in a silent tug-of-war between two invisible titans. On one side, dark matter's relentless gravity pulls galaxies together, weaving cosmic structure over billions of years. On the other, dark energy pushes back, stretching spacetime itself with a force that grows stronger over time. This battle isn't just shaping the universe today, it's writing its final chapter. Picture a pendulum swinging in slow motion, each arc a billion years wide. Right now, the pendulum is still high, with galaxies clustered and stars burning bright. But the energy driving that swing, dark matter's pull, is locked in a struggle against dark energy's push. If the pendulum slows too much, if dark energy's acceleration wins out, the universe faces a chilling fate, the Big Freeze. Galaxies would drift apart, their light stretching into oblivion as space expands faster than any signal can cross it. Star formation would sputter out, black holes would evaporate, and eventually, even the fabric of matter itself might unravel in the cold, infinite dark. But what if the pendulum swings the other way? Some theories suggest dark matter's gravity could gain the upper hand, pulling everything back in a cataclysmic reversal, the Big Crunch. Imagine the universe's expansion slamming into rewind, galaxies hurtling toward each other in a cosmic collapse hotter and denser than the Big Bang itself. It's a fiery counterpoint to the Big Freeze, one where the universe doesn't fade into silence but explodes in a final, searing moment, the wild card. We still don't know the true nature of either force. Dark energy might be constant, or it could evolve, growing stronger or weaker over time. Dark matter's influence could wane as the universe thins out, or its gravitational grip might hold firm. The answer lies in the delicate balance between them, a balance astronomers are racing to measure by tracking how fast distant supernovae recede, how galaxy clusters merge, and how the cosmic web stretches over eons. Every new observation tightens the constraints, narrowing the possibilities, but one thing's certain, the fate of the universe isn't just a philosophical question. It's a physical one, written in the invisible language of dark matter and dark energy, and as we decode their secrets, we're not just predicting an ending, we're uncovering the deepest rhythms of existence itself. Dark matter doesn't just live in the equations of astrophysicists, it's seeped into our stories, our art, even the way we think about our place in the cosmos. Take Philip Pullman's His Dark Materials, where the mysterious substance isn't just a plot device, it's a bridge between worlds, a metaphor for the unseen forces that shape existence. Or consider films like Interstellar, where the fabric of spacetime bends under invisible weight, mirroring real science while stretching the imagination. These narratives tap into something primal: dark matter, as the ultimate symbol of the unknown, a blank canvas for humanity's deepest questions. Philosophers and scientists alike grapple with what it means to live in a universe where most of what exists is fundamentally hidden from us. Dark matter challenges our most basic assumptions about reality. If we can't see or touch it, how do we know it's real? And if it's real, what else might be out there, just beyond the limits of our perception? This tension between the known and the unknowable has fueled debates from lecture halls to late-night conversations, turning dark matter into more than a scientific mystery. It's a cultural touchstone, a reminder of how much we still don't understand. Even in music and visual art, dark matter's influence pulses through creative works. Composers weave its themes into symphonies that evoke vast, empty spaces, while digital artists render galaxies haloed in invisible mass, making the unseen feel tangible. It's no coincidence that dark matter captivates artists. It embodies the same duality they so often explore, presence and absence, light and shadow, the visible and the veiled. What's striking isn't just how often dark matter appears in culture, but how it shifts the conversation. It forces us to confront humility in the face of the cosmos, while simultaneously sparking audacious ideas about parallel dimensions, hidden worlds, and the nature of consciousness. Whether in a physicist's lab or a novelist's studio, dark matter serves as a potent reminder the universe is far stranger, far richer than we'll ever fully grasp. And perhaps that's why it endures in our collective imagination, not just as a scientific puzzle, but as an invitation to wonder. Let's clear up some cosmic confusion. Dark matter isn't what you might think. Pop culture often paints it as a swarm of black holes lurking in the void, but those cosmic vacuum cleaners are made of ordinary matter, just compressed to extremes. Dark matter's influence is far subtler, a gravitational whisper rather than a stellar demolition, and no, it's not antimatter either. Those exotic particles annihilate in flashes of gamma rays when they meet normal matter, leaving behind signatures we'd easily spot. Dark matter doesn't blaze or collide, it ghosts through the universe, untouched and unseen. Another stubborn myth that dark matter is just a band-aid for broken physics, a placeholder slapped onto theories to hide gaps in our understanding. But here's the truth: while its identity remains a mystery, its effects are etched into the cosmos with undeniable precision. From the way galaxies spin to the cosmic web's intricate scaffolding, dark matter's fingerprints appear everywhere we look. It's not a scientific cop-out. It's a puzzle piece that fits so many observations. Dismissing it would mean throwing out decades of cross-checked evidence. The real challenge isn't whether dark matter exists, but helping everyone grasp why scientists are so convinced. Take the bullet cluster again. The way mass and gas separated during that collision can't be explained by tweaking gravity alone. Or consider the cosmic microwave background, its temperature variations matching dark matter's predicted distribution like a lock and key. These aren't hunches, they're multiple lines of evidence converging on the same conclusion. So why the disconnect? Astrophysics thrives on nuance, but nuance gets lost in headlines. When researchers say, "We don't know what dark matter is," it's mistaken for "we made it up." In reality, uncertainty is science's engine. It's how we push boundaries. Think of it like detectives tracing a suspect they've never seen. They've got DNA, footprints, even security camera blur, but the face remains hidden. The case isn't weak, the culprit's just that elusive. Bridging this gap starts with demystifying the process. Every time a telescope maps gravitational lensing or a simulation predicts galaxy formation, it's not blind faith, it's rigorous testing. And when alternative ideas like MIND emerge, they're not dismissed, they're scrutinized, refined, and weighed against the data. That's how science self-corrects. The public's curiosity is a powerful ally. It's up to us to turn dark matter is fake into dark matter is fascinating, and here's why. Because in the end, unraveling this mystery isn't just about particles or equations. It's about seeing the universe and our place in it with clearer eyes. What if dark matter isn't just part of our universe, but a visitor from another? Among the wildest and most tantalizing theories in cosmology is the idea that this mysterious substance might be a cosmic refugee, a leftover from other universes in a vast multiverse. Picture a foam of bubbling realities, each with its own laws of physics, occasionally brushing against one another. In those collisions, traces of matter, or something unlike anything in our universe, could have seeped through, lingering as the invisible mass we now call dark matter. It's a concept that blurs the line between science and speculation, but it's not pure fantasy. Some models of string theory and quantum gravity suggest these hidden connections could be possible, even if we'll likely never see direct proof. The beauty of this idea lies in its audacity. Instead of hunting for particles in detectors, we're forced to ask, could dark matter be the fingerprint of a reality entirely foreign to ours? Imagine a universe where gravity behaves differently, or where atoms never formed. If remnants of that alien cosmos drifted into ours, they'd carry none of the familiar signatures of ordinary matter: no light, no charge, just gravity's quiet tug. That would explain why dark matter seems to ignore every rule we know. It's not playing hard to get, it's playing by a different rulebook entirely. Of course, testing this is a monumental challenge. Unlike hypotheses that can be probed in labs or observed with telescopes, the multiverse idea lives in the realm of theory, stretching the limits of what science can verify. But that doesn't make it meaningless. Sometimes the most radical ideas act as intellectual scaffolding, pushing us to rethink boundaries. If dark matter truly is a whisper from another universe, it would mean our cosmos is far stranger than we imagined, not an island, but one thread in a tapestry of realities. And that's the real intrigue. Dark matter might be more than a puzzle to solve. It could be a doorway. Every unexplained rotation curve, every gravitational lens bending light where nothing visible stands, might hint at a grander architecture lurking just beyond our perception. Whether this theory holds or not, it reminds us of science's most thrilling truth. The universe's greatest mysteries often point to truths we haven't even dared to dream yet. Every year, research labs around the world pour billions into chasing an invisible cosmic enigma, a pursuit that might seem extravagant when weighed against urgent problems like disease, poverty, or climate change. Why invest in something as abstract as dark matter when those resources could feed millions or fund clean energy? It's a fair question, and one that scientists don't take lightly. But here's the counterpoint. The tools built to hunt for dark matter often spin off technologies that transform life on Earth. Take medical PET scanners, which trace their origins to particle detectors developed for physics experiments. Or the superconducting magnets in MRI machines, refined through research into high-energy collisions. Even the internet itself began as a way for scientists to share data across continents. The line between abstract discovery and tangible progress is often invisible until it changes everything. This isn't just about gadgets, though. Dark matter research pushes engineering to its limits, forcing innovations in materials, computing, and optics that ripple far beyond astronomy. Quantum sensors designed to catch elusive particles could revolutionize navigation, while ultra-pure crystals grown for detectors might unlock breakthroughs in battery technology. And let's not forget the thousands of engineers, programmers, and technicians whose skills, honed in the pursuit of dark matter, fuel industries from aerospace to artificial intelligence. The knowledge economy isn't just built on practical solutions, it thrives on the kind of boundless curiosity that drives fundamental science, yet the debate goes deeper than economics. Dark matter research taps into something primal, the human need to explore, to understand our place in the cosmos. History shows that societies investing in fundamental questions, why the stars move, what lies beyond the horizon, often reap unforeseen rewards. The sailors who mapped the oceans for trade routes also revolutionized navigation. The physicists probing the atom unlocked nuclear energy. Who's to say unraveling dark matter won't reveal new laws of physics or even technologies we can't yet imagine? That's the delicate balance at the heart of scientific progress. For every dollar spent peering into the void, there's a responsibility to ensure it serves humanity, not just in some distant future, but today. The best research programs bridge that gap, pairing cosmic ambition with earthly applications. When a dark matter lab develops a more sensitive radiation detector, it might end up screening for nuclear threats. When a telescope's imaging algorithms sharpen, they could improve early cancer diagnostics. The universe's greatest mysteries have a way of circling back to us, revealing not just how space works, but how we might live better within it. In the end, dark matter isn't just a scientific target, it's a mirror. How we choose to search for it reflects what we value as a species, our hunger for meaning, our knack for innovation, and our willingness to bet on the unknown. The critics aren't wrong to ask tough questions, but the answers might lie in recognizing that the frontier of knowledge isn't just out there. It's woven into the fabric of progress itself, pulling us forward in ways we're only beginning to measure. From the silver screen to streaming series, dark matter has slipped into our collective imagination, not just as a scientific concept, but as a storytelling powerhouse. Documentaries like Particle Fever immerse viewers in the high-stakes hunt for cosmic secrets, turning abstract theories into gripping human drama. Neil deGrasse Tyson's Cosmos transforms swirling galaxies and invisible matter into visual poetry, making the universe feel intimate and awe-inspiring all at once. These portrayals walk a tightrope, simplifying complex ideas without sacrificing truth, because when done right, they don't just educate, they ignite curiosity. But there's a catch. Dramatizations sometimes bend reality for the sake of narrative, leaving audiences with misconceptions. Imagine dark matter depicted as a swirling, glowing fog. It's cinematic, sure, but far from the intangible, ghostly reality. Or worse, scripts that blend dark matter with black holes or antimatter, muddying the waters. That's where science communication steps in, bridging the gap between entertainment and accuracy. Channels like Veritasium and PBS Space-Time thrive on this balance, using stunning visuals to explain the real science without dumbing it down. The goal isn't to drain the wonder, it's to ground it in fact. What's remarkable is how these stories resonate. A kid watching Cosmos might not grasp every detail, but they'll remember the thrill of discovery, the sense that the universe is vast and mysterious. That spark can shape careers. Astronomers like Vera Rubin or dark matter pioneer Simon White didn't start with textbooks, they started with wonder, often kindled by a documentary, a planetarium show, or a late-night gaze at the stars. Media doesn't just reflect science, it fuels the pipeline of future researchers, proving that storytelling is as vital to progress as any telescope or particle detector. Yet the responsibility cuts both ways. Creators owe it to their audience to get the basics right, because misinformation spreads faster than light in our digital age. A single misleading line in a blockbuster, say, dark matter as a weapon or sentient force, can take years of patient debunking to correct. The best collaborations, like those between physicists and Hollywood consultants on films like Interstellar, show how accuracy and artistry can coexist. When science and media align, they don't just entertain, they illuminate, turning the invisible into something we can all finally begin to see. Want to explore dark matter for yourself? You don't need a particle detector or $1 billion telescope, just an internet connection and a dash of curiosity. Platforms like Zooniverse have revolutionized citizen science by letting anyone sift through real astronomical data, hunting for gravitational lenses or odd galaxy rotations that might betray dark matter's presence. Imagine scrolling through telescope images on your lunch break and flagging a never-before-seen distortion, because that's exactly what hundreds of volunteers have done, contributing to published research without ever setting foot in a lab. It's science without barriers, where a teenager in Tokyo or a retiree in Toronto can help decode the universe's biggest mystery. For a more immersive experience, interactive simulations like the Dark Matter Universe Explorer drop you into a virtual cosmos where you can tweak dark matter's properties and watch galaxies form, or fail to, in real time. These aren't just fancy video games, they're simplified versions of the tools professional cosmologists use, revealing how tiny adjustments to particle mass or interaction strength ripple across cosmic history. Planetariums worldwide have embraced the challenge too, with shows like Phantom of the Universe using jaw-dropping visualizations to project dark matter's hidden architecture onto domed screens, making the invisible feel tangible. The learning doesn't stop there. Online courses from institutions like MIT OpenCourse, or Coursera break down advanced concepts into bite-sized lessons, complete with animations of galaxy collisions or animated explainers on gravitational lensing. Even YouTube channels like Minute Physics and Kurzgesagt have turned abstract theories into viral videos, using playful illustrations to unpack why dark matter matters. This democratization of discovery does more than educate. It transforms passive observers into active participants. When a high school student manipulates a simulation and sees how dark matter's gravity bends light, or when a book club discusses the latest dark matter documentary, science stops being a distant lecture and becomes a shared adventure. And in a world where misinformation spreads like wildfire, that's priceless. Giving people the tools to explore complex ideas first, and doesn't just foster wonder, it builds a society that thinks critically, questions boldly, and grasps the thrill of staring into the unknown. Because the next groundbreaking idea might not come from a lab-coated expert, it could spark from someone sitting at their kitchen table, wide-eyed, as they realize they've just glimpsed the invisible threads weaving our universe together. Throughout history, the unseen has always stirred both scientific curiosity and spiritual awe. Dark matter's elusive nature, its invisible grip shaping galaxies yet slipping through every attempt to detect it, has led some to ponder whether it's more than a cosmic ingredient. Could it be a fingerprint of something divine? For theologians and believers, the universe's hidden architecture echoes ancient ideas of a reality beyond human perception, where the physical and metaphysical intertwine. The Book of Hebrews describes faith as the evidence of things not seen, a phrase that, to some, resonates eerily with dark matter's ghostly influence. Others draw parallels to Hindu concepts of Maya, the illusionary veil separating humanity from ultimate truth, or Islamic teachings emphasizing the unseen dimensions of Allah's creation. Yet science and faith don't have to stand at odds. Many astronomers and physicists find their work deepens their spiritual wonder rather than diminishes it. Jesuit priest and cosmologist George Coyne, for instance, saw the hunt for dark matter as a sacred alignment of curiosity and humility, a reminder that the universe refuses to conform entirely to human understanding. The very mystery that drives scientific inquiry can also inspire reverence, a sense that the cosmos holds layers of truth waiting to be uncovered through both equations and contemplation. What's fascinating is how dark matter's ambiguity leaves room for dialogue. Unlike past conflicts where scientific discoveries upended dogma, dark matter's unknowns create a space where questions outnumber answers. Some religious scholars argue that if dark matter reveals anything, it's the poverty of rigid literalism. The universe is too vast, too strange, to fit neatly into any single framework, theological or empirical. Meanwhile, secular scientists often acknowledge that the word matter itself might be a placeholder for something beyond current paradigms, a humility that bridges the gap between lab coats and lecterns. The tension here isn't between faith and fact, but between certainty and wonder. Dark matter's shadowy presence challenges both atheists and believers to sit with discomfort, to resist the urge for easy answers. Whether one sees it as a cosmic code waiting to be cracked or a whisper of the divine, its persistence as a mystery reflects something fundamental about humanity, our need to search, to question, and to find meaning in the stars, even the ones we can't see. Cutting-edge technology built to hunt for dark matter doesn't just unlock cosmic secrets, it transforms everyday life in ways most people never see. Take those ultra-sensitive detectors buried deep underground, designed to catch the faintest whisper of a WIMP collision. The same materials and precision engineering now power advanced medical imaging devices, spotting tumors earlier than ever before. Or consider the cryogenic cooling systems developed to keep dark matter experiments running near absolute zero, tech that's revolutionized superconductors, making MRI machines faster, quieter, and more affordable. Even the machine learning algorithms sifting through mountains of particle data are being repurposed to diagnose diseases from medical scans, catching patterns too subtle for human eyes. The ripple effects extend far beyond hospitals. Dark matter research has spawned breakthroughs in radiation detection, with spin-offs safeguarding airports and shipping ports by sniffing out illicit nuclear materials. Those ultra-pure crystals grown for particle detectors, they're now improving solar panels and next-gen batteries. And let's not forget the global computing grids first built to crunch cosmic data, the ancestors of today's cloud infrastructure that powers everything from streaming services to AI. But here's the deeper truth: innovation doesn't follow a straight line. When scientists pushed to detect the undetectable, they didn't set out to invent better medical scanners or clean energy solutions. They were chasing pure curiosity, yet history shows that fundamental research, the kind driven by wonder rather than profit, often yields the most unexpected dividends. The World Wide Web began as a tool for physicists to share particle data. GPS relies on Einstein's theory of relativity, once dismissed as abstract math. Dark matter's legacy might follow the same arc, today's impractical experiments birthing tomorrow's essential technologies. Critics argue the billions spent on underground labs and space telescopes could be directed to immediate needs. But that's a false choice. The same labs training physicists to probe the cosmos are also training engineers who will design earthquake-resistant buildings or optimize energy grids. The pursuit of dark matter isn't a diversion from real-world problems, it's a catalyst for solving them in ways we can't yet predict. After all, you can't schedule a eureka, a moment. Breakthroughs come when humanity peers over the horizon, asking questions not because they're useful, but because they're there. And in that act of looking up, we often find the tools to better our lives below. At the heart of dark matter's mystery lies a tantalizing possibility, that its secrets are written in the strange, counterintuitive language of quantum physics. While galaxies and cosmic webs reveal dark matter's gravitational muscle, its true identity may only emerge when we peer into the subatomic realm, where particles defy common sense, existing in multiple states at once or vanishing in flashes of probability. Consider supersymmetry, a leading quantum framework predicting that every known particle has a heavier, invisible twin. If correct, the lightest of these sparticles could be dark matter, drifting through space untouched, their existence hinted at only by the equations of particle physics. But supersymmetry isn't the only quantum clue. Some theories suggest dark matter could be tied to extra dimensions, hidden layers of reality, curled up so tightly that only gravity can seep through. Picture a universe where what we perceive as dark matter's pull is actually ordinary matter brushing against invisible folds in spacetime. Other models propose quantum fields beyond the Higgs, humming through the cosmos with an energy we've yet to detect. Each idea, no matter how abstract, shares a common thread. Dark matter might not just be a particle we haven't found, but a shadow cast by physics operating at scales and dimensions we can scarcely imagine. The stakes couldn't be higher. For decades, physicists have struggled to reconcile quantum mechanics with gravity, two frameworks that work flawlessly in their own domains but clash violently when forced together. Dark matter could be the bridge, a missing link revealing how the quantum world's probabilistic dances give rise to the cosmic ballet of galaxies. Experiments like the Large Hadron Collider aren't just hunting for particles. They're testing whether spacetime itself holds hidden symmetries or extra dimensions that might birth dark matter naturally. What's exhilarating is how these quantum possibilities transform the hunt. If dark matter emerges from theories attempting to unify all forces, its discovery wouldn't just solve an astronomy puzzle, it would crack open a new era of physics, exposing layers of reality we didn't know existed. Imagine learning that the universe's invisible architect was hiding in plain sight all along, woven into the quantum fabric we've been straining to understand. That's the promise and the provocation of this quantum frontier. Every flicker in a detector, every anomaly in a collider, could be the first glimpse of a deeper truth, one that redefines not just dark matter, but everything we thought we knew. Dark matter isn't just a gap in our knowledge, it's a glowing invitation to push the boundaries of what we think is possible. For nearly a century, this invisible enigma has defied detection, yet its fingerprints are everywhere. In the whirl of galaxies, the warp of starlight, even the birth of the cosmos itself. Every telescope pointed at the sky, every particle detector buried underground, is part of a grand human experiment to answer one of science's oldest questions: what is the universe truly made of? The pursuit has led us down unexpected paths, rewriting the rules of gravity, conjuring hypothetical particles, even flirting with the idea of parallel dimensions. Yet the mystery endures, a humbling reminder that for all our progress, the cosmos still holds cards close to its chest. What makes this quest so extraordinary isn't just the potential payoff, it's how the search itself has transformed us. Dark matter has become a crucible for innovation, forcing breakthroughs in technology, computing, and collaboration on a global scale. The same detectors designed to catch elusive particles now safeguard borders and hospitals. The algorithms built to sift cosmic data help diagnose diseases. Even our language has evolved, with terms like dark sector and shadow universe creeping into mainstream culture, proof that the unknown captivates us all. And perhaps that's the real lesson here. Dark matter's greatest gift isn't just the promise of discovery, it's the way it keeps us questioning. Every null result, every dead end, sharpens our tools and refines our theories. The night sky isn't a static backdrop, it's a living puzzle, and we're piecing it together one observation at a time. With next-generation telescopes like Rubin and Euclid set to map the cosmos in unprecedented detail, and quantum sensors nearing atomic-scale precision, we're closer than ever to pulling back the curtain. So whether dark matter turns out to be WIMP, Axions, or something beyond our wildest conjectures, the journey matters just as much as the destination. It's a story of persistence, of humanity staring into the void and refusing to look away, and when the answer finally comes, when the invisible is unmasked, it won't just solve a scientific riddle, It'll remind us that the universe is stranger, richer, and more wondrous than we dared imagine. Until then, keep looking up. The dark has secrets to share, and we're just beginning to